Hi, to start today, I'm going to give you a little surds and indices quiz. You'll get 4 answers, A to D, and you'll have about 20 seconds for each question. Maybe a bit shorter, maybe a bit longer. Just, some take a little bit longer. Here goes. So get some paper, and then you don't actually need to pause the video. You can just watch this play out. So, what's the answer to this? Okay, about 5 seconds. Right, no answers yet. Just hopefully you've made a note. How about this one? 5 seconds. Third question. Bringing in some indices. Five seconds. This question here, back into subtracting surds. Okay, 5 seconds. All right, next one. Five seconds. Of course, you can pause it if you need a bit longer. This one. Okay, 5 seconds. This is the last one. Five seconds. And relax for the moment. Right. Let's look at the answers, and I'm going to go through them. So, first one. Just remember what I did now. So, here we go. Answer was D. Reason is that when we have this, okay, if you write out in full, then it would be 3 root 5 times 3 root 5. We'd multiply the 3's to give 9. We'd multiply the root 5's to give 5. That gives us 45. Quicker way of doing it is to just square the 3 and square the root 5 and multiply them together. So that's again going to give 9 times root 5, i.e. AB to the power n is equal to A to the n, B to the n. All right, that's going to come in indices, but it's one to be familiar with. Well done if you got that correct. Next one. The answer is B. We multiply the powers out to give A to the power of minus 12, and that means 1 over A to the 12. Standard form is this one here. It's a bit like when you do, so I'm going to give a similar example. If I do 7 times 10 to the 6 plus, let's just do 1 times 10 to the 6, this is actually 7 million plus 8 million. Sorry, 7 million plus 1 million, and I get 8 million. I basically, because these powers are the same, I don't worry about them when I'm adding them. It's like I've got 7x plus 1x. I get 8x. It's just that x is 10 to the power 6. So that's what you can do to add standard form without a calculator. You should be doing all this without a calculator. I didn't mention that, but that was, yeah, that's implied because I'm testing your understanding. We can put all these things in a calculator, but it's whether you understand it or not. When the power is different, you have to make the power the same. And actually the easiest thing to do is turn this into 0.07 times 10 to the 102. I add 2 to the power here, and I divide by 100 here, so it is the same. And then that becomes plus 8 times 10 to the 102. And I'm back in the same position. I'm going to add these two together, 8.07, and then the power stays the same. This one here. The answer was A. Okay, using the knowledge from before, we're going to bring this largest square number out, and that is actually 9. So it's going to be root 9, root 7. That will give us root 63. Over here, don't forget about the 5. It's going to be root 4, root 7. That gives me 4 times 3, which is 12. And 4 times 2. I'm rooting the 4 and I'm rooting the 9 here, which is 10. Root 7. And that's going to lead to 2 root 7. How about this one? Well, the answer is B. So if you take on board what I said before, the a, b, all to the power n is a to the n, b to the n. We can do the same thing here. That's going to be the easiest thing. So it's going to be 2 to the 3 times a to the 6, because I'm doing a squared all to the power 3, times b cubed all over a to the 5, b to the 5. The a to the 5 and the a to the 6 are going to mostly cancel and just be left with a. Same happens here. The b to the 3 is going to mostly cancel with that. I'm going to be left with 2. 8a over b squared. So it's one again. The answer is actually 60. So the best way to deal with this is to write it as root 4, root 3, that's my root 12, times root 3, root 5, that's my root 15, times root 4, root 5. And what we see is we've got 5 times 4 times 3, which is 60. So we don't need a calculator for this. We can deal with the surds without. Finally, one with a fractional index. You may have forgotten this, you may not have. The answer is 4 over 9. So what we can do first of all is write 8 to the power 2 over 3 divided by 27 to the power of 2 over 3. Now we've got to remember what these things mean. So 8 to the 2 over 3 can actually be written as 8 to the 3rd squared. There's this rule of powers, which is x to the a to the b equals x to the ab. I'm sort of just doing the opposite. I'm getting back to x to the a all to the b. So this becomes 8 to the 3rd all squared. Now 8 to the 3rd is actually the cube root of 8. You've got to remember that. So it's the cube root of 8 squared. Cube root of 8 is 2. 2 squared is 4. And that's where that 4 came from here. 27 is very similar. 27 to the 2/3 is going to become 27 to the 3rd, then squared. And 27 to the 3rd is the cube root of 27, which is 3. 3 squared is 9. So we get a final answer, 4 over 9. Okay, if you got all those correct, fantastic. If you didn't, all right, think about whether you understand it. You might want to practice this another time or go back and try some of the questions. I kind of made this lesson while I'm doing surds. We will look at indices later on. So don't worry too much about the indices ones if you haven't studied them yet, but make sure you're on top of the surds. The main focus of today's lesson on surds is rationalizing the denominator. And the denominator is this thing here. The top one is the numerator. Let's just add that actually. And what this means is that at the moment, the denominator is irrational. It's got a square root of a number and it's a surd on the bottom. And we want to somehow make the denominator rational. So it's like a whole number essentially. So words to the effect of make an equivalent fraction to 1 over root 2 in which the denominator is rational. That's the same as saying rationalize the denominator. Now you might already think, I know how to rationalize the denominator, but we're going to do some other stuff as well. So don't just leave quite yet. All right, 1 over root 2. How can we rationalize the denominator? Well, we can, remember, with fractions, we can times top and bottom by the same number and we don't change it. So we could times through by top and bottom by 2, or we could divide through by 2. We could times through by 10, for example. Now, how can we get rid of that root 2? Well, what we can actually do is we can times it by root 2 over root 2. Because it then becomes root 2 on top, because it's 1 times root 2, and 2 on the bottom. So I've successfully rationalized the denominator. Now I've said that, can you try these next 3? And then think about how you might generalize it. What do I mean by generalizing? Like a general sort of rationalizing the denominator procedure as such. I'll explain a bit more what I mean in a minute, but I want you to think about what generalizing means. So 1 over root 3, hopefully you've tried these, is going to be 1 over root 3 times, right? And then we're just going to times by root 3 this time, not by root 2, because that won't help. And we're going to get root 3 over 3, so very similar. For this one, we're going to times, funnily enough, by root 6 over root 6. That's probably the best way to do it. You can, in theory, do other things. So then I'm going to get 10 root 6 over 6. This time we're not quite finished. I mean, it doesn't say in the question to simplify it, but it's always good practice to simplify. So I can actually divide top and bottom by 2. It's going to be 5 root 3 over 3. 7 over root 7 times through by root 7 over root 7, which is going to give me 7 root 7 over 7, which actually just becomes root 7. And that makes sense, doesn't it? If I have a number and I divide by its root, I'm going to get back to the root because when I times the two roots together, I get the number itself. And what I meant by generalizing was that if I say had a over root b, this is what I mean by generalizing. It could be any surd here. I could times, or maybe I should just say equals first. It's going to be a over root b, and then I'm going to times by root b over root b, and it's going to become a root b over b. I've rationalized it, assuming that b is a whole number. We've rationalized in general. It gets a bit trickier here because now I don't just have a nice surd by itself, like root 2 or root 7. I've actually got a sort of a whole number and I'm subtracting a surd or adding a surd. How can we deal with this? Well, the issue is if you times through by 3 minus root 2, top and bottom, let's give it a go. Because that might be your initial thought. Then when you work that out, you're going to get 3 minus root 2 on top when you do that multiplication. Don't forget, you're basically doing a 2 bracket multiplication here, and you're going to get 9 minus 3 root 2 minus 3 root 2 plus 2. And we've still got a surd on the bottom. We've not actually rationalized it. So this this doesn't work. How can we manage to get rid of the third? What can we times by to somehow cancel it out? Well, here's the answer. You can actually, let me just delete that. You can actually take your 1 over 3 minus root 2 and times it by 3 plus root 2 over 3 plus root 2. And we'll see why that works. Because now we're going to be left with 3 plus root 2 on top. And then I'm going to get 9. And if I do my cross multiplication, it's going to be plus 3 root 2. Because I've now, I get a plus, but now I get a minus 3 root 2. And they're going to cancel out. Fantastic. And then I'm going to be minusing 2. So for my final answer, I'm going to get 3 plus root 2 all over 7. That's it. We've rationalized the denominator. And you got to admit, that is nicer. Like dividing by a horrible, horrible third, or having a third at the top and just dividing by 7. That is easier to deal with. Okay, try this next one. It's going to be the same process. So 1 over 5 minus root 3, and then I'm going to multiply top and bottom by the same thing. It's going to be 5 plus root 3. Which is going to leave me 5 plus root 3. Okay, don't be afraid to put brackets around it to help you do that. So I'm going to get 25. And then plus 5 root 3 minus 5 root 3. So actually, I don't even need to put it in. I can just basically square the 5 and then subtract the 3. And that's going to leave me with 5 plus root 3 all over 22. And this one here, very similar. But now, instead of timesing by 2 plus root 7, I've been timesing by that. I'm going to change the sign again, so it's going to be 2 minus root 7. So it's the same idea. It's probably like how you would think about doing it. I'll talk a bit more about this in a minute. But yeah, I got 2 minus root 7 on top. And then when I multiply it, I'm going to get 4 minus 7. I've actually got a negative on the bottom. 2 minus root 7 over minus 3. And what we can now do is we can actually times top and bottom by minus 1. And essentially flip the signs around. It's going to be root 7 minus 2 over 3. You really should, if possible, get rid of negatives like this. It just is more simple. I mean, I guess the rule in maths is always have as few kind of symbols as you can. And like I'm using the same amount of symbols here as here, except one less. Actually, that minus is gone. Now, one way you could have done this without doing that step is there's no reason why you should have multiplied by 2 minus root 7. You could have multiplied by, I could swap these around and it'd be root 7 plus 2. And then if I times through by root 7 minus 2, you wouldn't have had to do that extra little step. You have to realize to do that. And because we wouldn't get a negative then, because root 7 is bigger than 2. Whereas we times through by negative here. 2 minus root 7 is a negative. So just something to be aware of. If you have a plus there, you can actually swap the third around. That would have been a different option. And generalizing. Okay, this is something I didn't make you do in this. I was just getting the general principle across. You could also have a third or a number, like a non-third, in the top, and then you would have to multiply that by 2 minus root 7. So let's say I changed this to 1 plus root 3. You would have had to have done 1 plus root 3 times all this stuff, and it would have quite messy on top, and you might have simplified. Just saying, okay, not like I didn't put it here just for simplicity. To generalize, I suppose it would be A over B plus or minus root c. Let's just write plus root c. And then I'm just trying to develop your understanding here. What do we do to top and bottom? We would actually times through by b minus root c. That will sort it out every single time. I'm not going to carry on with the calculation here. It's just getting you to think, like, what can I always do in this situation? And basically, you times by the bottom, but you just flip the sign. That's the main bit of the lesson, I'd say, but actually a little bit more creeps in. When we solve, a little while ago we would have solved equations like this. This is an equation with x on both sides. We tend to say we don't really, when we get to A level, we don't write the steps down, but we would minus 3x on both sides to give 1 equals 2x plus 4, then minus 4 from both sides to give minus 3 equals 2x, divide through by 2, x equals minus 3 over 2. Kind of the same idea here then, except I've got some surds in place. So now I've got root 2x and 2 root 2x. So this one's bigger, so actually my third step would be to minus root 2x. And actually, that's going to leave me root 2x plus 5, because I've got 2 lots of root 2x. If I minus a root 2x, I'm just left with 1 lot of root 2x. Then I would subtract 5 to give minus 2 equals root 2x. And finally, I would divide through by root 2. The only thing is, in this case, if I was asked to maybe leave it in the form k root 2, which could be the case, even that I should maybe have added that, then we'd have to realize that we have to rationalize the denominator. And we can, again, this is returning to what we did near the start. I can times through by root 2 over root 2. So it's going to become this. I've times the top by root 2 and the bottom by root 2. The bottom becomes this. And that's going to leave me with minus root 2, which is the answer. I'm done. Okay, so yes, okay, if you're not asked to rationalize the denominator, you could leave it like that. This is definitely simpler. You might be asked to leave it in this form, k root 2. You might want to think about how you could generalize that. I don't think I'm going to go through that here, but how could you generalize and solve these general surd equations? Which leads us finally and nicely into simultaneous equations. You might think, how is that related? Well, we're going to solve one with surds in. That's going to be good. Just to remind you then, solving simultaneous equations, if we have equal coefficients here and they're opposite, we just basically add them together. We add the left-hand sides together to give us 6x, and we add the right-hand sides together to give 15. So x is going to be 15 over 6, which I can simplify. I can divide through by 3. It's going to be 5 over 2. Okay, I gave a fractional one here. That's all right. So I can substitute that back into either one. I think I'll substitute it back into this one. So I'm going to get 5. I've done 2 times 5 over 2, which is just 5. 5 minus y equals 2. That's going to give me y equals 3. I haven't really done it by rearranging it. I've just looked at it and seen that I could check my answer if I wanted. This is 2.5. If I times that by 4, I get 10. 10 plus 3 is 13. It definitely works. All right, if you're feeling confident, give this one a go. Otherwise, I'm going to go through it. Right, now, what can we do here? We want to make the coefficients equal, which they're not at the moment. Well, I'm going to give a suggestion, I think. I could actually divide or times through by root 2 to make this a bit nicer. Maybe it's a little bit easier to times through by root 2. Let's divide by, I'm going to divide by through by root 2. So I'm going to have 5x minus 3y equals 41. Not going to change that one. And then I'm going to be left with 7x plus 4y equals 82 over root 2. I basically made it so the left-hand side's a lot nicer. Okay, yes, the right-hand side is a third. Now I need to make the coefficients equal, so I'm going to times this one by 4, this one by 3. So I'm going to get 20x minus 12y and then I'm going to have to times that through by 4. That's going to be 164. Times this one through by 3, 21x plus 12y equals 82 times 3. 80 times 3 is 240. It's going to be 246 over root 2. Don't forget about that root 2. Add these together. I'm going to get 41x equals 164 plus 246 over root 2. It's not looking particularly nice, that, is it? Until we realize that 41 does go into these numbers. If I divide through by 41, this is just going to leave me 4. And this is going to leave me 6. So I'm going to be left with 6 over root 2. I might finally want to rationalize the denominator, which would give me 4 plus 6 root 2 over 2. I've times through by root 2 over root 2. Or 4 plus 3 root 2. We're there. For one of the values at least. And then I can substitute that back into either one. Probably best to substitute it back into the one that's not got surds in it. So it's going to be 5. Let's write this out. It's going to be 5 lots of 4 plus 3 root 2. I've just substituting for x minus 3y equals 41. That's going to give me 20 plus 15 root 2 minus 3y equals 41. What should I do here? I will add the 3y onto both sides and minus the 41. So it's going to be minus 21 plus 15 root 2 equals 3y. Divide through by 3. We're going to get y equals 5 root 2 minus 7. Okay, I've just divided minus 21 by 3 and written it to the right, and I've done 15 root 2 divided by 3, which is 5 root 2. Bit trickier, where I've used the idea of rationalizing the denominator. There might be other ways you can do this. I think that's a pretty solid way. If you start trying to times through, you can make the numbers the same by timesing through by 4 root 2 and this one 3. I don't know, that might work, you know, as long as you've got a solid way. That was a pretty solid way, I think. Whew, that's it for now. So we've rationalized the denominator for surds like when there's just root 7 in there, root 6 and so on. Sometimes we have to do a little simplification after. When we've got ones like this, okay, just swap the sign around. We've looked at solving equations and we've looked at solving simultaneous equations. Make sure you are confident at manipulating surds with and without a calculator. Well done.